with normal, hyponormal, and PP operators from Hilbert spaces. I restricted myself to the compounded operators from Hilbert space. There will be some difficulties if we want to consider unbounded case. I shall mention that when I get the point. First, if H is a Hilbert space, already know the algebra for bounded operators on H. For an operator A, we have the null space and the range. Usually, the null space becomes normal because it is always closed, and the range is not necessarily closed, and it is one more difficulty, and several more solutions must be done before we get the result. I is the density operator, we have ordinary unit production, and the construction of the adjoint operator or the evolution, although some results can be done without evolution. Now, recall the definition of the median, normal, or unitary operator in the space. Good ordering of the median operators. Of course, I need to mention that A and B should be written before we can find the ordering. And one generalization of normal operator, one of many. A is a hyponormal if A star A is greater or equal to A star, or the other way around, A is called co-hyponormal if they can switch their places. Very important inclusions. If operator is everything, then it is normal. If it is normal, then it is hyponormal, and it is co-hyponormal. Now it is written in red. In finite dimensional Hilbert spaces, the notion of normal operators is the same as the notion of hyponormal or hyponormal operators. And of course, if basic Hilbert space is infinite dimensional, then you don't have the opposite conclusion. There are hyponormal operators that are not normal, or equivalent to co-hyponormal operators that are not normal. What we most frequently do in mathematics is numerical theory. It is a problem to how to find an ordinary inverse of a given operator. A to the power of -1 such that its elementary equalities are satisfied. The first difficulty we find even in linear algebra settings. If you have complex square matrix, it is not necessary that you can find the ordinary inverse. And even in more general case, if we have a complex matrix which is rectangular, then we certainly do not have ordinary inverse. In this case, and in many other cases, it is useful to consider generalized inversion. The most frequent way is to write several equations which are satisfied by an ordinary inverse, in the case when it exists. Take some of these equations and say, for example, we can consider only the first equation and say that x is an inner inverse of A, or take several of them. But now we have several problems. The first problem is the uniqueness. How to find appropriate equations to get the unique generalized inverse, or we have, even if we have the uniqueness, it is very difficult, more difficult to compute with generalized inverses than the ordinary inverse, which is more effective. Now, if we get 1 to 4. Here is well known and probably the most known inverse. It is the Moore-Penrose inverse. And again, it is written in red. The Moore-Penrose inverse is unique in the case when it exists, and it is frequently denoted by a dagger. And for a complex rectangular matrix, the Moore-Penrose inverse always exists. We have +1 difficulty for the most simpler case. When we consider a linear bounding operator on a Hilbert space, then the Moore-Penrose inverse of A exists if and only if the range of A is closed. Now, this is the point of difficulty. If this subspace is not closed, then this operator exists again, but now it is not bounded. It is absolutely defined operator, and it is not difficult to work with. For example, if we have some other equations, 2, 5, and 6, we obtain the Drazen inverse, which is also unique in the case when it exists. I recall the equation 6, where we have some n to appear. And the smallest such n is known as the Drazen index. To see what the Drazen index really is, let us consider the square complex matrix. The simplest case, A is a complex n by n matrix, and it naturally has the Jordan canonical form. In a Jordan form, we have a block corresponding to 0 eigenvalue, and the Drazen index is the same as the representative index of this block. This block has many zeros, and it is nilpotent, and the index of this nilpotent is the Drazen index. Among other things, I asked myself when these two most important indices coincide, or equivalently when the Moore-Penrose inverse commutes with the starting operator. The commutativity conditions seems to be very important. Many things go easier. The relationship between normal and EP operators. Normal operators are well known, EP operators are less known. If we have a normal operator with closed range, then it is necessarily EP operator. The opposite inclusion does not hold. We have EP operators which are not normal, even in a finite dimension of the space. It is pure linear algebra. Thank you. And what does generalized inversion allow us to do? If we have generalized inverses, or have operators with closed range, then we have this decomposition of Hilbert space, and these decompositions of an operator. We are going close to linear algebra again. We have lots of zeros. We have zero blocks. Of course, they are operators on infinite dimensional Hilbert spaces. But we have, for example, in this case, A1 to be invertible in ordinary sense. Then all generalized inverses we can obtain inverting the operator there on those subspaces where the ordinary inverses exist. It is a very useful block of decompositions of operators. This is the third one, similar to previous. Now we have the essence and descent of A. We have this chain. The null space of A contains always the trivial null space, and when we iterate the power of A, we get in general larger and larger subspaces of the starting Hilbert space. And the essence of A is the smallest n when we get to once we get the equality, we have equality to the end. And similar for descent. And the descent of A is the smallest n such that we have such equality. Once we have equality, we can have equalities later. And now we have very important result. If the estimate and descent of A are finite, then they are equal. For this statement, we don't need a norm on a Hilbert space. It can be a linear space and linear operators on a linear space. But we have to have that A is everywhere defined. So again, we have difficulties which close linear operators which are not defined everywhere. So this very important result, which I use later, is not applicable for closed operators. Classical rail Hilbert space. We have the left shift, A is the left shift, B is the right shift, and these are some relations. These are relations which will be counterexamples to the questions which we like propose later. And it is important to mention that A is hyponormal and B is co-hyponormal operators which are not normal. Left and right shift are the most important examples of hyponormal operators which are not normal. Now I have results. Of course, bad English. The assumption that A have a closed range is enough to prove that the following conditions are equivalent. The first one says that the operator A is normal, and in the rest we have some various conditions involving the star, the evolution, and the full parallel inverse. What I would like to avoid are, for example, conditions in 5, 6, and 7, when I have some extra conditions concerning the tracing index, the descent or the ascent of A. And the previous example shows that these conditions cannot be avoided easily in infinite dimensional settings, which is of prime interest to me. If these conditions can be avoided only if we have a finite dimensional Hilbert space. Here also the statement is noticed by 9. Part of the statement deals with the ascent, and this condition cannot be avoided, and I have example before. For a finite rank operator, I have two more conditions. Also example of operators. I have also examples of operators which are not of finite rank, and these conditions are not satisfied. So the finite rank condition is essential here. Concerning hyponormal operators, I have the following result. I can prove that A is hyponormal even on if we have this instruction here. And finally, I think this is the last page. I'm very fast. This is the first result concerning co-hyponormal operators, and finally theorem, arranging the conditions which are equivalent for an operator to BTB, or generalized normal operator. All of them are proved using theory of operator matrices and according to the property that they have closed ranges. All of these results have recently been proved for finite dimensional settings using the properties of a rank of a complex matrix, and I extended these results in a different way to arbitrary Hilbert spaces. Some of them, sorry, one more sentence, some of them can be done without inversion. 9, 10, 2, and 3 can be done in settings more general than Hilbert spaces. Thank you.
Are there any questions? No comments? No. There is no one. Let's thank the speaker again.